Dr. G.S. Mahalakshmi, Assistant Professor, Department of Computer Science and Engineering, College of Engineering, Gindi, Anna University, Chennai. She has more than 13 years of UG and PG teaching experience and 5 years of research experience. She has so far contributed 85 research publications, and her research interests are Tamil computing, artificial intelligence, text, and web mining. She is an active member in UG and PG Syllabus Revision Committee and designed the syllabi for Anna University and affiliated engineering colleges for the following subjects: software requirements management, software quality assurance and testing, artificial intelligence, knowledge management, object oriented analysis and design, and Tamil computing. She has also authored several books, 2 journal papers, 31 book chapters, 3 lecture notes, 3 international conference papers, 36 national conference, and 10 other papers. Dr. G.S. Mahalakshmi is an associate editor of Mimanjari, an official magazine on Tamil computing from INFITT. The books of Dr. G.S. Mahalakshmi are Kanithal Adipadai and Kanini Moriyiyal in Tamil language.
Welcome to the UGC lecture series in computer science. In this lecture, we are going to discuss about page tables, the structure of page tables, their implementation, and the variations in page table. What is a page table? Page table is a mechanism or a data structure available as a part of your paging scheme. Inside the address translation mechanism, there needs to be a mechanism or a storing area where the correspondence between the page and the frame is stored in a hierarchy. We refer to this as page tables. There can be varieties in the page table structure. The number one can be hierarchical page table, or the second can be the hashed page tables, or the other alternate implementation can be the inverted page table implementations. Hierarchical page tables, from the name itself you can identify that there is a hierarchy in the implementation of the page table. The hierarchical page tables can be 2 level, 3 level, and multi level. Hashed page tables under this concept of mapping more than one frame to a particular page. Hashing works under the concept of buckets. Every bucket consists of more than one frames, and every bucket is mapped to a single entry in the page table. The third complex and yet another alternate mechanism is inverted page tables. Under inverted page table scheme, in addition to the correspondence between a page and a frame, the process ID is also stored along with the P, F pair. Therefore, the process which corresponds to this P, F frame can also be easily identified in an inverted page table. We will now discuss each one of the structure of page table in detail. Hierarchical page tables. Hierarchical page tables basically break up the logical address space into multiple page tables. The multiple page tables can be in terms of 2 level, 3 level, or any number of levels. As and when the levels of page table increases, the complexity or the time taken to access a particular page increases. As you all know, the one clock cycle is used to load the page table, and the next clock cycle is utilized for accessing the contents in the page table. Therefore, for a 2 level page table, basically the time taken to access the page table is multiplied twice. For a 3 level page table, it is thrice, and so on. Therefore, hierarchical page table scheme can only be extended to a 3 level hierarchy and not more than that. Therefore, we are now going to a hashed page table implementation. This is how a 2 level page table will look like. There is an outer page table and there is another normal page table which is available. This is the physical memory which is available. Therefore, this normal page table in a simple paging scheme is now visualized into 2 different levels. The set of addresses or bits which are corresponding to the page entry in a page table is now divided into two different entries, and the higher entry corresponds to an outer page table, and from the outer page table an inner page table is identified, and every entry in the outer page table corresponds to one inner page table, and maybe if this is identified as the entry in the outer page table, the corresponding inner page table is loaded and the entries are accessed. This is how a two-level paging scheme works. In two-level paging scheme, basically a logical address, assuming we are working on a 32-bit machine with 1K page size, the logical address is divided into a page number consisting of 22 bits and page offset consisting of 10 bits. Remember, the logical address is a combination of page number and page offset. Because this is a 32-bit machine with 1K page size, 10 bits is allocated to offset and the rest higher order 22 bits are allocated to page number. Page table is also paged because we are following a two-level paging scheme. The page table is also paged, and therefore there needs to be a outer page table, and therefore we extract a 12 bit out of this 22 bits. We extract only 12 bit for the page number and 10 bit for the offset. This 12 plus 10 corresponding to the 22 bits as a page offset. In this paging example, two-level paging example, this is how the organization of bits in the logical address is there. The page offset always corresponds to the displacement, which is indicated as D as in any other simpler paging scheme. The difference lies only in the P area or the page number area. Here the page number is divided into a PI and a P2. PI is an index to the outer page table and P2 is the displacement within the page of the outer page table. This is how the address translation in a two-level paging scheme would work. Here is the logical address P1, P2 and D. P1 and P2 corresponding to the page number. As and when the logical address is getting generated by the CPU, the displacement D is kept aside for later use to add with the frame as and when the frame is identified. This P2 is also kept aside. Initially, this P1 is taken and referred to an outer page table. The distance from the start address of the outer page table up to P1 will give you the location of P1. The reason is the entries in the page table are always arranged in a linear hierarchy. Therefore, the entry in P1 is identified directly and the correspondence to the base address of the inner page table is also identified. Therefore, now you can understand that as many entries are there in the outer page table, that many inner page tables will be available, or that many inner page table base addresses would be available. Therefore, loading the base address which is identified in this location will actually give you or will actually load you the second level of your page table. As and when the second page table is loaded, you now take the P2 and identify that entry in the second page table. Here also the items or elements are arranged in a linear fashion, and therefore this corresponding entry in the P2 will give you the base address of the particular frame, and therefore the next level page table is loaded and the frame could now be located at this place. This is how the address translation happens inside a two-level paging scheme. If it is a three-level paging scheme, the only variation is that the outer page table is again paged, so that here comes one more level of a page table, which we will discuss in the future slides. This is how the three-level paging scheme is visualized. Here is the two-level paging scheme. So, therefore, there is an outer page and an inner page, P1 and P2 corresponding to the page number and the offset. In a three-level paging scheme, the offset is retained as such and inner page is retained as such as 10 bits. However, the outer page, which corresponds to 42 bits, is now separated into 32 bits as the second outer page and 10 bits as the inner outer page or next level of our primary outer page. This is how the 3-level paging scheme is organized. If you want to go for 4-level paging, again this particular outer page will again be paged and it could again be separated. But however, it is not recommended because as we said before, the memory cycles taken for every access into a page table and the loading of a page table is a important matter of consideration, and therefore the speed or performance of the operating system would be affected if you choose a n level paging scheme. Therefore, modern days operating systems only go for 3-level paging, and beyond that they follow yet another scheme for variation in paging. And this is how the hashed page tables would work. Hashed page tables basically work under a common feature that in a single page more than one frames are getting mapped on. Therefore, in the page table only the virtual page numbers are getting hashed. This is how the algorithm in hashed page tables work. Fundamentally, page table contains a chain of elements hashing to the same location. These elements would be the frames. Virtual page numbers are compared in this chain searching for a match. There would be more than one element possible, and therefore obviously there would be a match found in the chain of elements available. If a match is found, the corresponding physical frame is extracted. If a match is not found, as usual in the paging mechanism, a page fault is generated. This page fault will be sensed by the operating system by the generation of a trap, and the page fault is handled at a later time using different mechanisms. Those handling mechanisms would be discussed in the future slides. This is how a hashed page table implementation looks like. This is the logical address, and which has the combination of P and D. D is saved for future use as such, and this P is given as input to a hash function by the hashed page table algorithm. The result of the hash function gives you the entry into a hashed page table. This entry, when interpreted, would contain many buckets like this. In either one of these buckets you can identify the corresponding frame, and remember, all these buckets are arranged in a hierarchical fashion by using the linked list data structure. This would ideally be a singly linked list or a linear list. Therefore, the frame identified from the bucket is now given back to the area where it is getting added with the displacement, and the real physical address is generated. The main difference between hashed page table and the hierarchical table is saving of memory cycles in loading the page table and accessing the page table. However, there is a limitation in this. There cannot be numerous buckets loaded into mapped into a same frame. There is a restriction on the number of buckets getting mapped or number of elements in the chain which is getting mapped to a single location. Therefore, only to a certain extent this hashed page tables could be used. Therefore, there is another mechanism recommended to the operating system in terms of inverted page tables. Inverted page tables work in a totally different manner unlike your hierarchical or hashed page tables. In hierarchical or hashed page tables, the D is kept aside and only P is analyzed for finding the frame number. However, in inverted page tables, both P, D are utilized along with the process ID, and therefore directly the frame number could be taken. This gives you yet another saving in your memory cycle. Therefore, for implementing the inverted page table, though it is complex, it increases the performance of your operating system. In inverted page table, there is always one entry for your real page inside the memory. Every entry contains information about the process that owns the page. Therefore, decreases in memory needed to store each page table. However, increase in time is needed to search the table. The caution is, whenever needed, use hash table, otherwise go to inverted table. This is how the inverted page table works, the process ID P are inside your logical address. The process ID P pair is extracted and is searched inside the page table. The location where this PID P pair is found, the I, is actually taken out and the I is added with your D to generate the physical address. Remember, we still retain the D, we only identify the PIDP. The location where PIDP is there is your frame number. This is how the inverted page table differs. We will now go for a break. We will resume the lecture in a few minutes. Welcome back after the break. We were discussing about the inverted page table implementation. However, there is a restriction in inverted page table scheme also. There has to be the number of entries carefully maintained across the process ID. As many processes are getting generated, the inverted page table grows larger in size. Therefore, there is a limitation to maintain the entries inside the inverted page table. There is another scheme recommended by your operating system to reduce internal fragmentation. This scheme is referred to as segmentation. So, in segmentation, this is recommended as an efficient memory management scheme because every block of sized memory pages is actually of variable size, unlike your paging scheme. In your paging scheme, every block of memory is of fixed size. Here it is of variable size, and of course, this reflects the user view of the operating system. That is, whenever the user demands a particular sized memory, that sized segment is allocated to the user process. Therefore, much lesser internal fragments would be generated. But anyhow, the internal fragmentation cannot be totally avoided in an operating system. What can be a segment? A segment is basically a logical unit as like your page. Anything can be a segment. The main program, procedure, functions, methods, objects, local variables, global variables, stack, symbol tables, arrays, and many other things could be inside a segment. The user view of a program would be like this. There will be a subroutines, there will be stacks, symbol table, main program, and the function you must have written a function to calculate a square root, which is actually indicated here as SQRT. This is how the user's view of a program would be there, and every component in the program would require different sizes of memory, and therefore segmentation is ideally suitable for the user's view of a program. The logical view of segmentation would go like this. This is a physical memory which is available, and the order of arrangement inside the physical memory goes this way. 1 is stored in the first location, and next 4, and followed by a vacant place, and 2, and then followed by 3. However, the user view is to combine all these components together to execute a particular program. Therefore, segmentation supports the user view of the operating system. Now, what is the definition of logical address in segmentation? In segmentation, again it is similar to the paging scheme. The logical address again here consists of 2 tuples. The first tuple is segment number. Remember, there we refer to as page number, and the second tuple is as usual referred to as offset. There we have referred to as displacement. Only the name differs. Here segment number and offset form a pair, and which are getting mapped to the 2-dimensional physical addresses. Where the segment number and offset will be available? In a table called segment table. Therefore, segment table has so many registers for its successful execution. As like page tables, every segment table should have a base address loaded into a particular register. This register is called segment table base register. There has to be another register called limits register, which tells you to what extent the table, segment table, grows inside the memory. This register is called segment table length register, which indicates the total length of the particular segment. The segment number S is said to be legal if it is less than the segment table length register. If it is greater than the segment table length register, obviously as an address generated the logical address is trying to access the address in somebody else segment, and therefore a trap would occur indicating the malfunctioning of a process inside the operating system. And this is how memory protection is associated with the segment tables. As like your page tables, here also there are valid and invalid bits called protection bits associated with the segment table entries. The valid or invalid bits are indicated by zeros and ones. 0 indicate an invalid bit and 1 indicate a valid bit. There could be an opposite policy around inside the operating system, indicating at 1 as a valid and a 0 as an invalid bit. It is how the policy differs. The protection bits are basically associated with the segments, and the sharing of code occurs only at the segment level. Therefore, the privileges on reading or writing or execution operation could be granted with the help of the protection bits indicated inside your segment table. Since segments vary in length, this could be the fundamental difference between the paging scheme and segmentation scheme. There in paging scheme there is no variation in the size of the pages, all are fixed. However, the segments can vary in their size limit. Therefore, memory allocation is a serious problem, and therefore we have to go for discussion of dynamic storage allocation while we discuss the segmentation related issues. This is how a segmentation hardware is implemented. As like paging, the CPU generates the logical address, and the logical address consists of a SES and D. And this D is actually taken, it is compared with the length of the STLR. If it goes beyond the length of the STLR, then a trap is generated stating that there could be an addressing error produced. If it is under the limits of STLR, then the control S is given, that is the a pass is given to the operating system asking it to proceed the segmentation implementation. Now the S is taken and it is identified in the segment table, and the base register or the frame number is identified, and both are actually accumulated together and along with the D, and it is generated as a physical memory address. And therefore, there is a fundamental difference you can notice between the paging implementation and the segment implementation. In paging implementation, D would be kept aside for addition at the later time. However, in segment implementation, D is actually taken initially and is analyzed, and the segment number corresponds to frame number is later identified. There is yet another variation which is recommended as to combine the paging along with the segmentation. Why to combine paging and segmentation? In segmentation, it's more advantageous than paging, but there is one problem in segmentation. Because of variable memory size, you cannot totally avoid the internal fragments, and the overhead involved in tracking the size of segments allocated is much more. Therefore, if you can visualize every segment of fixed sized pages, it would be more helpful. This is how the mechanism of segmentation and paging came into picture. The goal is more efficient support for sparse address spaces. Therefore, in this combined scheme, the logical address is divided into 3 portions as segment number, page number, and page offset. This is how the mechanism would work. The logical address generated has the segment number, page number as a combined area and the offset at another combined area. The selector, we call the combination of P and S as a selector. The selector loads the descriptor table, and in the descriptor table the entry of the selector is actually identified. The entry gives you the segment descriptor. The entry in the segment descriptor is taken. Remember, there would be many segment descriptors available in the descriptor table. Therefore, this segment descriptor which is now identified is taken and is compared with the offset, and the page corresponding page number is identified. This page is actually reserved for future use. Now, the address generated would contain 2 parts. Except the other than the offset, there is another part called directory part. This directory part is now loaded and it is analyzed, and the corresponding directory entry in the page table is actually identified. The register which takes care of the or which houses the base address of the page directory is called page directory base register. This directory base register is called and the base address is loaded, and therefore the page directory is totally is loaded inside the memory. Therefore, in the page directory the corresponding directory entry is identified, and that entry would correspond to the loading of the page table. That is, this entry would contain the base address of the page table. As many entries are here, that many page tables would be available. Therefore, this is a page directory. A directory contains the address of many page tables. One such page table is taken, it is loaded into the main memory. The corresponding page which is recommended is also taken, and inside the page table that corresponding page table entry is identified, which would now correspond to a frame number. That particular frame is loaded, and inside that particular frame the offset gives you the exact location of the physical address. This is how the combination of paging and segmentation scheme in Intel 3386 work. The implementation has one problem: what changes happen on a context switch inside your combined paging and segmentation scheme. It is tough to answer this in a single minute. It is a research problem, and therefore people have identified the implementations mechanisms with different varieties in the combination of paging and segmentation scheme. In Intel Pentium also they use the combination of segmentation and paging scheme. This is how the address translation in Pentium happens. The CPU generates the logical address, the segmentation unit which we discussed generates the linear address which is given to paging unit. The paging unit now generates the physical address, and therefore physical address can be referred to the physical memory. The one difference between Intel 3386 and Pentium is that the address translation is here segregated as segmentation unit and paging unit, and both are not mixed together. This is how the easy address translation happens. However, the memory cycles are much more than the Intel 386 kind of implementation. This is how the Pentium segmentation works. As like the Intel 3386, here also the selector is taken and is identified as an entry inside your descriptor table. The entry would give you the 32-bit linear address, and the offset is added along with this, so that the correct 32-bit linear address is generated. This is how the segmentation in Intel Pentium will work. The paging in Intel Pentium is also of the same style, except for two differences. The page directory in Pentium is working on two different size of pages, as 4 KB pages is also there and 4 MB pages are also there. Only for 4 KB pages an inner level of a page table is maintained. The reason is 4 KB pages would be much more than 4 MB pages. Assuming 1 MB contains how much KB? You can imagine that many 4 KB pages would be available. Therefore, to compensate the entries or to minimize the entries in the first level, we go for an inner level page table in Pentium, and the inner level page table only takes care of 4 KB pages. The 4 MB pages are directly maintained in the page directory. Otherwise, it is much similar to another simpler paging schemes available in other operating systems. This is how the 3-level paging scheme in Linux works on. Here is a global directory. The global directory entry is identified and it goes for a middle directory search. Middle directory entry is identified and it goes for a page table search. The page table entry is identified and it goes for a frame search. The frame is identified and the offset is taken along with this, and the physical address is getting generated. With this slide, we have now discussed different case studies across Intel 3386, Pentium and Linux on how the paging and segmentation works. We will now summarize what we have discussed in the lecture. In this lecture, we have been discussing the definition of page table, the varieties of implementation of page table, the types of page table hierarchies, hierarchical page table as 2-level, 3-level and multi-level, hashed page tables, inverted page tables and their benefits and shortcomings. We have also seen another variation on reducing the internal fragmentation. The solution is segmentation. Segmentation can be combined with paging and can be implemented to provide a faster access for your CPU. Therefore, many operating systems like Linux tend to use the combined segmentation and paging scheme which we have discussed in the case study. We will now go for discussing few questions. Number 1. Why is inverted page table implementation advisable? Question 2. How to improvise the performance of CPU with respect to paging? Question 3. What is so undesirable about the combination of segmentation with paging? Question 4. How to minimize the page fault? Question 5. What will the operating system do on occurrence of a page fault? With this, we have come to the end of this lecture. In the forthcoming lectures, we will discuss the schemes for managing the page fault and handling a page fault occurring inside the operating system. Thank you.